In modern radiation therapy, we see an increased use of small fields for treatments in highly specialized techniques such as IMRT, SRT, SRS, SABR, VMAT. And with increased use of small fields, performing patient-specific quality assurance becomes more challenging due to dosimetric challenges related to small field conditions. More specifically, the detector-related challenge of fluids perturbation effects. For a single detector, the black squares here represent the total fluids perturbation correction factor made up of 4 components, and the 2 components contributing most are volume averaging effects and material density differences between the detector material and the medium material. Density differences lead to changes in mass energy absorption coefficient ratios with decreasing field size, as can be seen in the figure on the left. And the figure on the right represents volume averaging effect, where the dashed line represents the measurement taken with a detector. It is not 100% equivalent to the actual profile as shown by the solid line. A novel scintillation-based dosimetry system, the Hyperscint RP200, developed by Medscint, has a sensitive volume of only 0.8 millimeters cubed, and it has a density similar to that of water, thus potentially resolving the fluence perturbation effects and also offering high spatial resolution. In this work, the Hyperscint RP200 was characterized for important qualities of small field dosimeters as outlined by the IAEA Technical Report Series 483. This dosimetry system showed excellent short-term repeatability with a standard deviation of only 0.04% for 10 readings. Also showed excellent dose response linearity all the way to 2,000 monitor units. We did notice a little bit of a small dose nonlinearity at really small doses of about 2.5 centigrade. So we saw 6% difference between the measured value and the value predicted by the linear fit. Medscint is aware of this problem and they are releasing a new software update. So hopefully that will be fixed or released shortly. The system showed no dose rate dependence for dose rates of about 100 monitor units a minute to 2,400 monitor units a minute, and also showed no dependence on the angle of irradiation for gantry angles of 0 degrees to 360 degrees. Additionally, field output factors were measured for field sizes of 10 by 10 centimeters, all the way down to 0.25 by 0.25 centimeters for 2 energies, the 6 MV energy beam and 10 MV flattening filter-free energy beams. When comparing to literature values, there was a really good agreement all the way down to 1 by 1 centimeters. And for the smallest field size reported in literature for comparable measurement conditions, we saw a difference of about 4%, and that was for 0.6 by 0.6 centimeters squared. So a Monte Carlo simulation of the detecting element would be helpful in helping to resolve the discrepancy that we saw. Overall, this characterization shows that Hyperscint RP200 with the 0.8 millimeter cubed plastic scintillator detector has desirable properties as a small field dosimeter and could potentially serve as a benchmark detector for small field measurements. Thank you so much to all the people that contributed to this research project and to all of the funding sources. We greatly appreciate this.